What is up, everybody? My name is Anthony. I'm an Eastern Orthodox Christian, and I come today to present another video on my Atheist Zeitgeist video, or on my Atheist Zeitgeist series. Today's video is going to be about methodology, and it's not exactly a fluid continuation from my last video, because my last video was unscripted. It was not exactly the most well put together or well thought out thing that I've put out thus far. There being like 3 things, but I did actually take the effort this time to script something, loosely speaking. I have the script here. There's a bunch of strikeouts and everything, so there's probably going to be some awkward pauses at times or some rambling at times. But just forgive me. I'm still working through the process of video production, so this is not exactly going to be a very fleshed out thing initially. Nonetheless, I do feel that I have some sort of leveling to play when it comes to the field of atheist scientific theory. So it is commonly known that atheists will utilize scientific arguments against theists. Little do they know that their own methodology is faulty. And I will be going into faulty methodology today, specifically about radiometric dating methods and geologic dating, or geologic column data. Geologic column data is mostly in the realm of fossils and dating fossils. I won't be getting into fossils. I'll be getting more into the actual methodology in which they produce the dates in the geologic column. So starting first with radiometric dating. Radiometric dating compares radiation in a specimen to a known decay rate. So if you take a specimen, right, specimen's going to have a specific amount of radioactive isotopes in it. You can take the amount of radioactive isotopes that are in it and compare it with background radiation or background isotopes and extrapolate an approximate time that the specimen was formed. This is called, this is just generally radiometric dating. If you know the initial conditions, then it's absolute radiometric dating. So if we took a specimen now, or that was formed now, and then in 20 years we tested it again, knowing the initial conditions, we would have an absolute decay rate in that specimen. What goes on is they take the specimen and they extrapolate a time from current data. So they don't actually take the initial conditions that the specimen was formed in, they take current conditions and extrapolate the data back. This is called relative radiometric dating. When you assume initial conditions, the current level of radioactive isotopes is going to influence the timescale in which the specimen will produce. There are 2 common methods of tracking radiometric isotopes. You have carbon-14 and uranium decay. Both of these methods are variable. There's no actual consistent timescale that you can use to determine the initial conditions, or to determine the amount of time that elapsed since the isotopes were formed, or since the specimen was formed. The production and decay of carbon-14 is dependent on the ionizing radiation of N2, or it's basically just 2 molecules of nitrogen. What happens is ionizing radiation splits the molecules apart, and it has neutrons to it. Well, actually, it takes away protons, and those protons essentially bounce around inside of the ionosphere. But by taking away a proton from each molecule, it becomes a carbon atom. And it's a carbon atom with 14 neutrons. It's a carbon atom with 14 neutrons. It's a carbon atom with an atomic weight of 14. Forgive my blunder there, but it has more neutrons than it should. It has 2 extra neutrons, I believe. Because carbon-12 is your typical carbon. So carbon with 6 protons and 6 neutrons. Carbon-14 has 2 extra neutrons. And it's an unstable isotope. And it's an unstable isotope, and it will decay naturally within a certain time frame. The amount of carbon-14 isotopes that are produced it's dependent on the amount of ionizing radiation in the upper atmosphere, which is dependent on the strength of the Earth's magnetic field. So with a decreasing magnetic field, you will expect to see more ionizing radiation, which means more of a certain isotope, or more of that isotope. So if you see a trend in the strength of the magnetic field, you'll see a reciprocal trend in the amount of ionizing radiation, and thus radioactive isotopes, specifically carbon-14. Next, with uranium. Uranium decays based on nuclear energetic bombardment. It also decays naturally. So any of these isotopes are going to decay naturally, but there are other factors involved which affect the manner in which that they decay. And it also affects the time in which they decay. So if you have bombardment of ionizing radiation, it can knock off neutrons. Then again, it could put the atom in a more stable position, but it could also split the atoms in the process of nuclear fission. If it goes through nuclear fission, it becomes 2 daughter isotopes, or it becomes 1 or multiple daughter isotopes. Like typically you'll have uranium. Actually, I haven't studied that. I haven't studied which daughter isotopes show up when uranium is decayed, but effectively, you can have effectively the way that the time scale is measured when it comes to uranium is you'll see what the distribution of daughter isotopes are. So if you have uranium that decays a level lower, that isotope will also decay, and that decay will branch down until you get to a stable isotope. Using the distribution of various materials within that specimen, you can determine an approximate age based on natural half-life. So if we're assuming natural half-life and we're not assuming any other conditions, you would expect to see a decay within a certain amount of time. So when we get these predictions of the age of the Earth, we get these predictions based on the natural half-life or the natural decay of uranium isotopes, which is where you get like the 3.5 billion number from. But there's also another factor to consider there. If the material is being bombarded by ionizing radiation or by high frequency, high energy radiation, it will induce fission. Same thing with if it's being bombarded by neutrons or being bombarded by charged particles. It will emit some kind of radiation and it will undergo fissure. Part of the reason why some of these dating methods when it comes to the natural half-life and natural decay of uranium, when it comes to determining the age of the Earth, is there's a lot of nuclear bombardment in space. There's a lot of ionizing radiation in space. You would expect to see a elevated decay rate in such specimens because of all that bombardment. And it doesn't give you it doesn't actually give you a good time scale because it can be so variable. Like you could have uranium decay within a certain amount of energetic bombardment within a few milliseconds, a few microseconds even. Not all decay conditions are going to be natural. But when you assume these decay conditions in a vacuum, you're obviously going to be getting timescales that are much larger because those things, the latent energy that goes into decay is, it takes a while to release that energy and to undergo fission in order to increase your energy potential. But a lot of that isn't actually considered when it comes to this because if you just take some specimen and measure the primary isotope and all the daughter isotopes, you can get some scale based on natural decay. But we're not exactly working with natural decay, so it's not entirely it's not a good systematic method. Well, it's not a good method when it comes to determining the age of things at all. But that kind of time is necessary. Like increasing any reason to increase the time scale is going to be a good one when it comes to these scientific proponents or atheistic scientific proponents, because their favorite phrase is that with more time, there entails more change. So if there's more time for uranium to decay, or more time for carbon to decay, or if we assume conditions where there's a lot of carbon, you're going to see over a large stretch of time that it's going to turn into a lot less carbon. But if you see a small amount of carbon or a small amount of carbon-14 in a specimen, it shouldn't make you immediately assume that there was the same amount of carbon-14 today at the time that specimen was formed. There's no way to know that. So there's no way to actually substantiate the claim that these specimens are hundreds of millions of years old, because we don't know the initial conditions. For all we know, the initial conditions could have been in a state where there's not a lot of carbon-14 to begin with. This is actually something that I will get into later in my next video, because the next video is going to be about electromagnetic dynamics and the Earth's magnetic field. But I might as well get into my next topic. My next topic is on geologic specimens and the geologic column. How do we determine time scaling on geologic specimens? So, like, how would these scientific proponents gather a scale of time for some fossil based on where it is in the ground? In the 20th century, the first experiments done on this subject involved taking boring samples and counting paramagnetic strata. So when certain ferric rocks form, they'll form in a manner, or they'll form with a certain crystalline structure that has a certain paramagnetic signature. And based on the signature, you can supposedly predict the age that specimen was taken in. This process would involve measuring magnetic strata in various low erosion areas, like above ground caves in Japan, which was actually done. And there was also boring samples that were done in the middle of the ocean towards various magnetic anomalies, also a topic I will get into in my next video. And they would extrapolate that data from the distance to various tectonic fissures. Typically, it's the one where they come together. I forget what it's called. But you have tectonic fissures that are faults You have some that come together that converge and some that diverge. Um, it's usually the ones where they converge and new material is pushed out, where you can kind of determine the if you can determine the age of something supposedly by measuring the distance to that, by also measuring plate movement over time and magnetic field polarity and their change therein. Plate tectonics and the addition of new material from fissures it can be substantiated. Sorry, plate tectonics and the addition of new material from fissures may be substantiated. We can measure seismic activity and observe material additions. Although if any data suggests otherwise, then I would be willing to change that view. But the crux in this, the crux when it comes to that side of things, is magnetic field polarity shift. And that is a big topic for another day. But this magnetic field polarity shift is a big proponent in using geologic specimens as a sort of timescale, or boring samples as a kind of a timescale. So if you can extrapolate the distance of certain strata, you can kind of determine at what area of time that strata was located in. If you could somehow determine a rate of expansion of the plates, or a rate of material addition in fissures, and a rate in magnetic polarity shift, then you can kind of determine the date from that. But magnetic field polarity is a big one that is just completely unsubstantiatable. If I'm to keep that kind of brief, it's basically fluid and thermodynamics that are involved with producing the Earth's magnetic field make it impossible for those reversals to happen. Just completely impossible. What we can observe is like a shifting of the magnetic pole, or the magnetic north pole. We can see that shifting around the our actual rotating axis. It kind of revolves around there. Sometimes it's like more narrow, sometimes it's more extreme, but we never see it flip. You see it kind of wobble around, but it doesn't flip. And it doesn't flip because it's impossible for it to flip. I will get more on the dynamics on that in my next video. But yeah. Yeah. I think that just about exhausts the content of this side of things. And I may take some time to formulate a better argument and write some kind of article that actually goes through in something a bit more of a conducive form, something that can be a bit easier to take in for some people. Is, with my sometimes verbal tics of like pausing or saying and stuff like that can be kind of a nuisance to people who are just coming into this, just coming across this information. They may think I'm just rambling about something because I'm not too well versed in speech like that. But I may put some of this in written form. It may start a Substack or something. Just keep looking at my posts if you can, and you can send me stuff on Discord. I am on Discord, very regrettably active on Discord. It's at Anthony Swampman, if I remember correctly. It is. I can post that all. At a different point. But you could probably send stuff to my email if you have questions about anything. My email is lokeen123@gmail.com. I don't have anything important on that email except for everything. I don't even care to. I don't even care to make that public because whatever. If you have questions about anything, send to that. Or if you know me on Discord, DM me or something, and I can go in a bit more detail about this. Because even though this was, somewhat scripted, I can certainly do better by putting something in a more written and more conducive form. But this leads me to the outro of this video, and question is, how will all of this tie into atheism? Call it a characterization, if you will, but many atheists I come across will levy science as an argumentation tool for anti-theist polemics, saying things like science denier or show me God data or the like. My purpose in forming this series is to expose scientific missteps in the grand narrative, which work to substantiate atheist claims about the genesis of the universe and the evolution of life, from archaebacteria to the genetic and phenotypical diversity we experience today. More details on this series to come. Anticipate my electromagnetic dynamics video and some going over ANOVA or fractional factorial analyses, because I did not go into exhaustive detail on this in my last video, but I do want to actually go through the process of using those in order to substantiate scientific hypotheses. All right, that leaves this video complete. Au revoir.